So the first one, conservation of what? You all remember us having Aldwin come up here and pull the masses in, and he sped up. Same thing that's going when the planets are orbiting the sun. When they come closer, they have to speed up because of conservation of angular momentum. Angular momentum means the momentum going around in a circle. Linear momentum would be the momentum going in a straight line. Okay, the next one. Why do astronomers want city lights to point down and not be excessively bright? You might recall that this is actually one of the objectives for the course, is for students to understand why this is a really serious issue to astronomers. Hence, we watched the video from South Park. Oh my God. That's even a step further beyond The Simpsons. The video from The Simpsons that illustrated in a humorous fashion the problem. So what is it that astronomers want? They want to see faint things in the night sky. What is it the city planners want?
To see in the night.
They want to be able to see in the night so people can get around safely, and it is a deterrent to crime. Now, there are solutions. For instance, I think our lights out here, they put a dome or a cap over the top to reflect the light down, because the city planners don't actually want to light up the sky. So it's more efficient to them if they reflect the light down, and it's better for the astronomers because the light's staying down. So, places like in Hawaii where they have all of the telescopes at the top of the mountain, they actually have island-wide restrictions on the light so the astronomers can do their astronomy without having light pollution from a mile below them on the island. So it was so the telescopes can see faint things in the sky. I hope nobody answered either. Some of these other things have a piece of truth and a lot of error. Things like so they can read their notes while working on their telescopes. Well, you do want to read your notes. Actually, something you don't know, but it's coming up in today's lecture. Actually, I say you don't know. I'm assuming you may know. Astronomers do not sit there looking through a telescope anymore. That's not what they do. In fact, it's not what they've done for a long time. They used to have cameras that photographed, and now they have digital cameras, what we call charge coupled devices, CCDs, the same thing that we have in our cell phones, and those allow them to do some much better work. And you can be in Lincoln, Nebraska, and controlling a telescope in Hawaii over the internet. So you don't even have to be anywhere close to the telescope. There are people at the telescope, they're the technicians, not the scientists. So these days, astronomers don't really have to worry about that. But the amateur astronomer, the hobbyist, or the person who, the hobbyist is, I was going to say, or the person who just likes to look through the telescope, that is the hobbyist. They usually are looking through a telescope then, and your eyes take time to get adjusted to the dark. You probably noticed that. You wake up in the middle of the night and you turn on the light switches and you're like, can hardly see. Then you turn off the lights and you can't see anything, whereas you could see fine before you turn on the
It's the worst when your dad puts on an automatic light inside the bathroom. You walk in there and say, "Oh, Lord, help me, please."
Well, see, in my household, we differ on this. I like to see the toilet when I go to the bathroom. My wife sits down, and so she never turns the light on. Different points of view. We would have a mess if I... Well, anyway, moving on. So having your eyes adjusted to the dark is an important thing if you're working in the dark. And so one thing that amateur astronomers will do is use a red light. So like you can download an app for lab, that shows you where the stars and whatnot are. And it'll have a night vision mode where it's just red and black, because your eyes are much less sensitive for the light adjustment to red light. And so the red and black helps you keep your dark adjustment. Going to the next one, which is untrue about visible light. Is light a wave? It has properties of the wave. That was the work by Thomas Young that said light has wave properties. Is light a particle? Has properties of particle. That was the work by Einstein. And so we have the wave-particle duality. It's both a wave and a particle. So neither of those was untrue. Skipping the correct answer. Can light be emitted and absorbed by electrons changing energy levels in an atom? Absolutely. And so the answer that was untrue was, and I'm crossing out the correct answer because it was untrue. That's the wrong range. That was false, yes.
Why did you just put false?
What?
Why didn't you just put false?
I know, I could have. The actual range for visible light is 400 nanometers to around 750 nanometers. Notice nano, that means 10 to the minus 9, not milli as I had there, and it's 400 to 750. Of these numbers, can you recall which one is red and which one is blue?
750 is red.
You're correct, sir. The long wavelength is red, the short wavelength is blue. Okay, then to our last question. What mechanism causes the sun to produce the vast majority of its light? Remember, I had 2 light sources out here at the end of the last class period. One of them was like the sun, giving off a continuous, glorious rainbow of colors. And that was the light that was giving off light because it was hot, which we call incandescence. Electron excitation would be absorbing light, not giving off light. The sun does have that going on in its atmosphere, but of course that's absorbing light. Electron de-excitation, giving off light as electrons fall to lower energies, that's also happening in the sun's atmosphere, but it's a very, very small amount of light compared to the vast amount of light because it's hot. And then this one here is just as bogus as, as a Raider loss. Just doesn't happen. I don't know if you guys saw the game yesterday. We were really lucky.
It's okay. The Patriots won. I don't care what else happens.
Okay. And finally, the last one. If we were talking about the moon, the last one would have been correct. The moon doesn't produce any light. It's a mere reflector. But the sun definitely is producing light. Any questions about the quiz? Did you all score above 75%? Which, I guess that's above 75%. That means, did you all get 100%? Probably not.
I got 75%.
All right. Okay. The electromagnetic spectrum. The spectrum of light. We've talked about light, 400 nanometers to 750. We will loosely use the word light to talk about the entire electromagnetic spectrum, but technically it's not light if our eyes don't see it. So visible light is technically light.
So that's very subjective.
Excuse me?
That's very subjective.
It's a little subjective on what's visible and what's not. But the term...
I mean, what counts as light on that?
Oh, technically it doesn't count as light if it's outside of visible range. But between friends, because light is an example of an electromagnetic wave, we start using the word light to mean electromagnetic waves. So, starting here with the longest waves. Radio waves are the longest waves. If you're listening to an AM radio station, you might be listening to an electromagnetic wave, well, a signal carried by an electromagnetic wave, that has a wavelength that's as long as a kilometer long, or kilometer, if you want to pronounce it correctly. So radio waves are very long waves. What are good things about these long waves? Well, one good thing about the long waves is they can go right through dust and clouds. So that's a good thing about those long waves. Another really cool thing about those is neutral hydrogen atoms give off radiation that's in the radio range. Hydrogen atom. What is present in a hydrogen atom? It has a proton at the center and electron. It's the simplest thing out there. So you have an electron going around a proton. There's the naive model making it look like the electron's doing a circle. Well, it turns out the electron has what we call spin. And if you hear the term spin, you would get the idea that the people who came up with the idea had. They noticed that the electron behaved like a magnet. it had what we call a magnetic moment. And they said, well, because it behaves like a magnet, it must be spinning. A charged particle spinning behaves like a magnet. And so they proposed that the electron is spinning, and they called its magnetic moment the spin. Well, we know more about electrons now, and we know it is not possible that the electron is spinning to make its magnetic moment. So when we talk about electron spin, we are not talking about anything spinning. It's a misnomer. What we're talking about is magnetic moment. So the electron behaves like a magnet with the north pole and the south pole. The nucleus behaves like a magnet with the north pole and the south pole. And if the electron's magnet and the nucleus's magnet are lined up, you have one energy state, and if they're anti-aligned, you have a different energy state. There's a small energy difference between the two, and when the electron is excited and goes to the higher energy spin orientation, it will then de-excite and give off radiation, electromagnetic waves, with an energy difference, or with energy equal to the difference. And that energy is so small, remember E equals HF, very small e means very small f, but wavelength is speed of light over f, so very small frequency means very large wavelength. So you have radio waves produced when the electron spin flips. What does this all mean? Right? Because we're in astronomy, we want to know that there's a basis for it, but we also want to know why it's useful. It means that using radio waves, you can actually map out where we have clouds of neutral hydrogen gas in the universe. So it's very useful. It's a way to actually map out neutral hydrogen gas. You can't see it with light. That's visible light, but you can see it with the radio waves. Microwaves, you're getting just shorter waves. Shorter waves we use, well, I'll show you examples of microwave pictures. Actually, if you look up here, these are examples of pictures taken in the different ranges. So this is, excellent, a picture taken with radio waves in the far right. The microwave background radiation is really, really interesting. It was proposed back in the 1940s that if the Big Bang occurred, that there should still be radiation traveling everywhere in the universe that was given off by the hot, dense material when the universe became transparent. They called the time when it became transparent, it's really something. Now I can't remember the word even. Excellent work, Richard. Well, it's around 300 to 500,000 years after the Big Bang, according to theory. And so theory says you should have this radiation traveling through the universe. Now, at that time, the radiation would have been super hot, but the theory goes further to say that the universe has expanded and the wavelength should be like 1,000 times longer than they were when it was emitted, which puts them in the microwave range. It puts them with the calculated temperature of around 2.7 kelvins. 0 kelvins is absolute zero. So the temperature it puts them at is really, really cold. Well, they didn't have any kind of telescopes at the time that could look at microwave radiation, and so they gave up. They gave up on looking for this sign of the Big Bang that theory predicted would be there. But then in the 1960s, when scientists were working on developing microwave communications so we could have our cell phone networks, they were trying to identify sources of interference so that they could find ways to remediate the problems with communication. And they found the signal that no matter what direction they aimed their microwave telescope, it was there. And it turned out they were observing the microwave background that had been predicted by the Big Bang theory. And so that's what this picture is that microwave background. And so the understanding of scientists is when you're looking at that, you're looking at how the temperature was distributed throughout the universe at the recombination. That's what the word was, which is not an appropriate word because it's not recombined, it's combined for the first time. It's when the electrons and the protons combine to form neutral hydrogen. So there is a great use for microwaves. Then we have infrared. And I just always have to point out that when I was a child, we read the encyclopedias in my family. We came to America, my parents bought World Book Encyclopedia, and all of us kids read them all the way through. And so when I got to this one, I just thought it was infrared. Made sense to me. But it's not infrared. It's infra as in below red. And so infrared, it's below red. You and I are giving off infrared radiation right now. If we had night vision goggles, we could turn off all the lights and we'd be able to see each other. Why? Because we're giving off radiation because we're hot. Do you remember the term for giving off radiation because you're hot? Incandescent. We are giving off incandescent light, the same as a traditional light bulb you have in your house. Those traditional light bulbs, of course, are going away. You can no longer buy less than 100 watt incandescent light bulbs because they're only 5% efficient at producing light. Where's the rest of the energy go? Heat, making things hot. Well, you don't put a light bulb in your house to heat your house. There are better ways of doing that. And so if you change to fluorescent light bulbs, the fluorescent light bulbs are somewhere in the ballpark of 30% efficient, which is not great, but 6 times better than incandescent. And that's the reason that you can't buy the lower power incandescent anymore. It's not some great government conspiracy. Okay, then we have the visible. Everybody's aware of visible light. So let's go on the other side. Ultraviolet light. Ultra is above. So this is light that has a frequency above violet, which is the highest frequency we can see. Infrared, below red, the lowest frequency we can see. And so ultraviolet allows us to see really energetic things going on. X-rays, and gamma rays are kind of special. But that's the electromagnetic spectrum. It goes through all of those. X-rays go through your body. Radio waves go through your body. But light waves don't. Right? Different electromagnetic waves behave differently with material. Why do X-rays go through your body? They have so much energy. Why do X-rays, not X-rays, radio waves, well, they're just so big, your body is meaningless to them. They basically go around it. Okay, our first clicker question. God bless me. You can answer starting now. Why is ultraviolet radiation more dangerous to humans than infrared? I was just going to say this and I didn't because I have too much time. I will answer while you're answering. Ultraviolet radiation has a high frequency. Because it has a high frequency, the energy of a particle for ultraviolet radiation is large because of that high frequency. Why is that important? I mentioned it on Friday. Ultraviolet light has enough energy that it can break bonds. And when it can break bonds, it can mess with you. And so ultraviolet radiation is a much bigger concern than radio radiation, a much bigger concern than microwave radiation, such as your cell phone uses. So go ahead and answer. We only have 4 people who've answered so far.
I would, but I can't.
You can answer on that.
I don't have a license for this.
If you have a license for the clicker, you have a license for that. I'm serious. You just have to log into the, download the software, I suppose. I know you're probably not going to get it done today, but it's an option. Okay, everyone but Aldwin's in, so.
It's my phone for the next couple days.
There's what we got for the breakdown. So obviously I wasn't clear enough either in my answers or in my discussion. Ultraviolet radiation doesn't pass through our bodies. It gets absorbed. Right now, X-rays do pass through. Ultraviolet is both a large category and a small category, depending on how you look at it. Technically, anything from ultraviolet through gamma rays would still be considered ultraviolet, but we usually break it down and say X-rays go from here to here, gamma rays go from here to here, and then the rest of ultraviolet is what we just call ultraviolet. And so with those definitions, the ultraviolet doesn't go through. But it can be absorbed and cause damage. So having enough energy for a photon to ionize material, does it say material? Enough energy for a photon to ionize. It doesn't say what it ionizes. This is actually related to one of your homework questions. One of your homework questions asks, what does it mean for a photon to be absorbed and take an electron's energy level from n equals 1 to n equals infinity. N is telling you its energy level. N equals 1 is the ground state like we talked about last class period. N equals 2 would be an excited state. So you've raised the energy. 3, 4, 5, you just keep raising the energy. Well, electrons are bound. And when we talk about energy, to say it's bound, we say it has a negative energy. Electrons bound to a nucleus have negative energies. If you raise the energy up to 0, then they're free to go. And so how do you raise it up to 0? Well, you have to have a photon that has energy bigger than that negative energy magnitude that it was in. So if it's in the ground state n equals 1, and you give it enough energy to be free, it's no longer in a countable energy state. Right? It hasn't gone from n equals 1 to n equals 3. It's gone from n equals 1 to it's free, which n equals infinity corresponds to the limit between bound and free. So if it says it goes from n equals 1 to n equals infinity, it means you've raised the electron's energy up high enough for it to escape. And if the electron escapes, that's what we call ionization. You've taken an electron away from the nucleus. So that's what happens with the ultraviolet radiation. It will ionize atoms. It will kick electrons off of atoms. And when it does that, it usually breaks bonds in the process. So that's what that homework question is dealing with. Any questions about this? I feel like I am more confusing people than helping people, and I don't want that. We're clear? All right. Excellent. Temperature. We've talked about temperature a little bit. Temperature is a measurement that tells us about the average kinetic energy of molecules. So low temperature means very slow motion of molecules. Absolute zero means that they have come as close to stopped as they can. Now, temperature scales, we have the Celsius scale and the Fahrenheit scale. Fahrenheit scale, developed by, what is it, Georg Fahrenheit or something like that. And it uses, for its low temperature calibration, the temperature of like freezing seawater. If you have ice and seawater mixed together, that would be the 0 Fahrenheit. And it uses body temperature for 100 degrees Fahrenheit. If it goes from 0 to 100, we call that centigrade. Remember, centi means 100. So it's a centigrade scale, but it has some serious flaws. Because what happens if you put more salt in your seawater? It's going to change the melting temperature. And so you have to have just the right combination in that seawater to repeat. And likewise, body temperature, if I have a fever, my body temperature goes up. So that's not a very good calibration either. So Anders Celsius, being a fine Swede, I'm a quarter Swedish, and I consider myself Swedish because that's the biggest single group within the Scandinavian, which I'm half Scandinavian. Okay, so Anders Celsius, he said, let's go with reproducible things. So he used pure water at its freezing temperature and at its boiling temperature. Very reproducible. But Anders did something silly. He said, let's make the temperature of freezing water 100 degrees and the temperature of boiling water 0 degrees. That was silly because temperature is telling you about how fast the molecules are going. He had a higher temperature meant they were going slowly. And so when he died, other people flipped it over to what we know today. That his was also a centigrade scale, 0 to 100 for his calibration, but his was much more reproducible, and that's why that's the one that scientists have moved to. Now, these days, the Fahrenheit scale is simply calibrated off of the Celsius scale. It's 32 degrees Fahrenheit is defined as 0 degrees Celsius, and the ratio of a Celsius degree to a Fahrenheit degree is 9 to 5. If it goes up 9 degrees Fahrenheit, it goes up 5 degrees Celsius with exact numbers. So the Fahrenheit is really just using Celsius and converting. Well, there is a minimum speed. In theory, the slowest something could go would be at rest. Quantum physics says, well, that's not reachable. But there's an absolute zero, which is the minimum motion attainable. And so that's where Lord Kelvin's temperature scale comes in. Lord Kelvin said, okay, let's make a scale that has zero is absolute zero. So if everything goes to its lowest possible energy state, essentially stop, we'll call that absolute zero. And so it turned out there was minus 273.15 degrees Celsius was absolute zero. And that's 0K, not OK. Of course, you could have thought that 0, 1 less than. There we go. So 0 kelvins, you don't use the degree sign with kelvins, is minus 273.15 degrees Celsius. Absolute zero. And you can see here on the temperature scale, temperatures when water freezes, boils, temperature of liquid nitrogen, temperature of the sun. Here's the temperature of the sun at its core and at the photosphere, at the surface. So temperature is telling us how rapidly the molecules are moving. Why is that important? Because things like the sun. Now this picture, I love this picture. These things right here are things that Galileo Galilei noticed on the sun. Storms, if you will, in the sun. And those storms, it's kind of hard to tell from these pictures, but if you analyze them carefully, you find they come in pairs, and we'll study all about them, I think, soon, when we talk about the sun. But the sun is giving off radiation because it's hot, so we call it a black body. Remember from Friday, black body because black is the ideal color for emitting or absorbing light. And the sun behaves as a black body at a temperature of 5,800 kelvins. I didn't bring out my toys again, but I pointed out on Friday, when I increased the temperature of the incandescent bulb, what happened to the brightness? If it got hotter, what happened to the brightness? It got brighter when it got hotter. What about the colors? Remember when it was low temperature, you didn't see blue. Got higher temperature, you saw lots of blue. So you have two things that change with temperature. One is the brightness, and one is the range of colors it produces. So this picture here, first of all, the picture on the left is just to give you an idea of a stove. Black is relatively cool. Doesn't mean you can touch it without getting burned, mind you. But if it's red, you all know, wow, that's really hot. And so the colors change with temperature, and it turns out blue is the hottest color. The hotter things get, the shorter the frequency, or the shorter the wavelength, the higher the frequency, and the more blue it's going to look. On the other side of the scale then, red is the coolest color. The cooler things get, the more it moves to red until you can't see it anymore. So that's why when I had that lamp out here, when I had it at a low temperature, it looked orange because it was relatively cool. And as I heated it up, it went through to a whitish color. And if I could have heated up more, it would have gone to a bluish. Now, where do you see this? Headlights in a car. You guys have seen those blue halogen headlights, right? There's also cheap knockoffs that just use blue filters. But what's the idea with the blue? Well, you have a halogen light bulb, which is an incandescent light bulb. It's a filament of tungsten. You put electricity through it and you make it super hot. That's what was going on here. That's what's going on in your car's headlights. So where's the halogen coming? They put a halogen gas in there in the bulb, and that small amount of halogen, when it is cool, it will attach to the tungsten. And so you'll have a molecule that has a tungsten and a halogen gas flying around. When it gets close to the filament, the high temperature makes them break apart, and so it drops the tungsten back at the filament. And so that halogen actually rebuilds the filament, which means that you would be able to do two things. Either make a light bulb that lasts for virtually ever, or make one that you burn at a higher temperature. And so that's what they do with halogen bulbs. They burn them at a higher temperature, which makes them wider. And then they have metal halogens, which is a different gas that has a metal halogen that will actually allow them to, it's a better getter, it's better at grabbing the tungsten and bringing it back, which allows you to go to higher temperatures, and so you can actually have a blue color because they're so hot. Question?
Which gas do they use?
Honestly, I don't know. It has to be a halogen, which means it's fluorine, chlorine, bromine, iodine. Well, it's not going to be one of the ones below that because it's radioactive, but it's one of those, but I don't know which. So when you see a car with bright blue headlights, they're bright because they're really hot, and they're blue because they're really hot. Both those things tell you they're really hot. Well, two people, Veen and this is just saying that it's giving off light because they're going really fast and hitting each other hard, and each collision produces light.
I remember you saying that the sun is white light, and so it includes all the colors, right?
Yes.
But if the sun is hot, I think it was like almost 10,000 degrees at the surface, and why isn't the sun blue?
Okay, so the sun's temperature, this picture here, this is the same picture, just on a different slide. This is the temperature of the sun, 5,800 kelvins. And this shows it as fairly yellow.
Okay.
That yellow is actually a little inaccurate. It's more white than yellow. But our atmosphere, we have what we call Rayleigh scattering. Rayleigh scattering is when you have particles that are smaller than the wavelength of light going through. And when that happens, when light interacts with those particles, the short wavelengths or the high frequencies interact much more strongly and just get redirected in all kinds of directions. We call it scattering. And so blue light gets scattered in all directions. So if you look in the sky somewhere away from the sun, you're going to see that scattered light because light from the sun went over there and then got scattered down to you. So that's why the sky is lit up during the daytime, because we have an atmosphere and it's scattering blue light in all directions. If you look directly at the sun, of course you're seeing the sunlight, but you had a bunch of that blue light that was scattered out in different directions. So if you take the sun's basically white light and you take away the blue, it makes it more yellow. And so the color of the sun is actually not nearly as yellow as we think it is because we have the Rayleigh scattering taking away the blue when we look directly at it. And we look in the other direction, we see the blue that was removed from sunlight going other places. Did I answer it?
Yeah.
And then 5 more things afterward. So this shows the sun is yellow, but it's, like I said, it's actually more white when you get down to it. In fact, I will show a picture of the spectrum of the sun. You'll be able to see it doesn't look nice and smooth like this because of gases that absorb and scatter light. So 2 laws here. Veen's law. Veen's law simply says, now there's an equation that goes with it that we will learn, that you'll use in your homework, one of the homework problems. The hotter body is, the more strongly it will emit at shorter wavelengths. It actually says the wavelength of peak emission, this is on the next slide, by the way, is equal to 2.9 times 10 to the, I think it's 9, but I could be wrong. Kelvins times nanometers divided by the temperature in kelvins. So it's a simple relationship. If you know the temperature, you can calculate the wavelength at which it's at a peak. So you look in this picture, this one here has a peak wavelength that is very short because it has a high temperature. This one here is a longer wavelength, this one even longer because the temperatures are cooler. So it doesn't show you, the temperatures are shown up above, and so we can calculate the number looking at those temperatures, but it's going to be on the next slide. And so it's easy to calculate. In fact, on the next slide, when we have the equation, so I have the right number for sure, we'll do a calculation. Then there's the Stefan-Boltzmann law. The Stefan-Boltzmann law talks about how bright it will be. And the Stefan-Boltzmann law says that the luminosity, the amount of light that it gives off, is equal to a constant called the Stefan-Boltzmann constant times the emissivity. The emissivity is equal to 1 for stars. So in astronomy, we just don't write it down because it's equal to 1 for the stars. They're perfect emitters. Times the surface area multiplied by temperature raised to the 4th power. Now this temperature has to be in kelvins again. So 0 kelvins would give off no radiation. My body is somewhere around, somewhere around 300 kelvins. I think it's around 310 actually kelvins. So if my body is 310 kelvins, I can use this to calculate how much radiation my body gives off. And of course, notice it has a surface area, so my body being a bigger surface area than most of you, that means that I'm going to be giving off, for the same body temperature, more radiation because a bigger object. So those are the two equations that we have. So it's 10 to the 6 instead of 10 to the 9. Got it. So Wien's law, let's calculate the wavelength that you give off for maximum radiation. So your body temperature is about 310 kelvins. Now we could go through and calculate it, but let's not worry about it. So if your body temperature is 310 kelvins, if you take this and you solve it for the wavelength that's at its peak, multiply both sides by wavelength max, and divide both sides by temperature. So I multiply both sides by this, and I end up with notice the kelvins here are going to cancel. The unit K will cancel with K. And I have 2.9 million divided by 310. Get this handy calculator out and the light so it'll work. 2, 9, 1, 2, 3, 4, 5. Stay with me, baby. Divided by 310. If this calculator works, which is a question, that's 935, I think 48567 it shows. This doesn't show any decimal points. We can do the calculation more carefully in our heads, probably than with this. So let's do it with the scientific notation. 310. That's 3.1 times 10 raised to what power? What power is that? Not supposed to ask how many of you are education majors? Just one. Well, they certainly taught me in my education classes not to ask what we call whiplash questions, where you start it as a declarative statement and then turn around to say, so what is? So instead of doing it that way, start at the beginning. What is 310 kelvins in scientific notation? 3.10 times 10 raised to what power? 2. So I have 2.9 divided by 3.1. That's going to be 0.9, as we can see, 0.936. And then I have 10 to the 6 divided by 10 to the 2. 6 minus 2 is 4. So it'd be 0.936 times 10 to the 4th, or 9.36 times 10 to the 3rd nanometers. Putting it into standard form, that'd be 9.36 micrometers. That's not visible. Question?
And just to clarify, nanometers is referring to the. Is it the what is the nano? Is that the wavelength that it's referring to?
Yes.
Or
so nano is 10 to the minus 9th. So a nanometer is 10 to the minus 9 meters. So let me there's two different ways of writing 9.36 times 10 to the third nanometers. It's 9.36 micrometers. Micro, that's the Greek, mu, is 10 to the minus 6, or then 9.36 times 10 to the minus 6 meters. That's not the visible spectrum. That is not between 400 and 750 nanometers. It's longer than 750 nanometers, so what range does that put our body's radiation in? It's not invisible. It's infrared. And so we're giving off infrared radiation. So if you have night vision goggles, what those night vision goggles are doing is they're actually taking a picture of infrared radiation, radiation that our eyes can't see, but that's being emitted. And then it takes that picture and it produces a picture in visible light. They do this through things like, once again, things like a phosphor or something. You absorb the energy into something that's going to then give off a visible light when it's absorbed. The other one, the Stefan Boltzmann law, I just wrote on the previous page. Notice with this, like the question on the weight of a telescope lens, the luminosity is proportional to temperature raised to the fourth power. If I were to double the temperature, so if I went from T1 is equal to, let's say, my body temperature, and then I double it, how much brighter would it be? How much brighter would my body be if I just doubled the temperature?
It's a lot brighter.
A lot is correct. It's going to be 2 raised to the fourth power. So 2 times 2 times 2 times 2, that's 16. So if I doubled my body's temperature, I'd be 16 times brighter. And the wavelength that I'm at my peak at, if I doubled the temperature, it would cut it in half. That still wouldn't be visible, but it would be, getting somewhere where I might give off a little bit of glow on the extreme, because remember, you have these tails out here. If the tail is bright enough, it could be giving off some visible light still. So those are both necessary for the homework problems. Students asked me beforehand, but I think they said, the last 5-ish I hadn't covered yet. Well, this is covering things that are in the homework. Here's the value for that constant, the Stefan Boltzmann constant. And just a number to boggle your mind. The sun puts out 64 million watts per square meter. So think about the sun. Its surface area is very many square meters. And it's putting off 64 million watts per square meter. It's really giving off huge amounts of energy. All right, our second and clearly final clicker question. What color indicates the hottest temperature of a black body? Alan? Oh, because you don't have your clicker. I'll just call on you when we're done.
I could be wrong, so.
It's okay.
I'm gonna fool myself.
There is nothing wrong. I was just reading one of my son's high school teachers, Jesse Rail. They asked, what was your hardest class? It was chemistry. I stayed steady, and I had to get over the feeling that if I answered wrong, that I was an idiot. Because if you already know the stuff, why take the class? Okay, so we had 8 said blue, 1 said white, and 2 said black. Which one would you go with, Alvin?
I'm gonna go with white.
Okay, why?
The just I don't have a really good example. I can't really say it. I don't know how to describe it. I think it's white.
Okay, now I'm going to finish by describing what white is, and then we'll see why it's not the right answer. Okay, white is the color we get. No, don't feel bad, man. White is the color we see when we have all 3 of our cones activated by similar amounts. Our eyes have 3 kinds of cones. They're called cones because they're shaped kind of like cones. And one cone is most sensitive in red. Well, let's put blue for the one that I put in blue. One is most sensitive in, I used to have green on here. There we go. One is most sensitive in green, and one is most sensitive, that's supposed to have been red, in red. So we have tricolor vision, red, green, and blue. That's why the three primary colors of light are red, green, and blue. If you mix them all roughly equally, so if these are all equal, then our brain interprets it as white. So white is what our brain says the color is. We have roughly equal amounts of both, which means for incandescence, the peak is going to be somewhere in the middle. The peak will be somewhere around here for that whitish color, like the sun is. But if it's super hot, then the peak comes over and you have the peak somewhere out here, and it's going to look really blue. If it's cool, the peak will be out here and you'll only see the red.